Doing problem 2 from section 6.2. So this is another optimization problem, the last one. Campground owner has 1,400 meters of fencing. He wants to enclose a rectangular field bordering a river with no fencing needed along the river. It says let x represent the width of the field, find the value of x leading to a maximum area, and find the maximum area. So I've got a picture of the situation here. Let's say that this is the river. We're no fences there. We're going to put a fence here, here, and here to enclose this area. It says to let x be the width, so I've done that, and then I've identified this length here to be y. So again, as usual with optimization problems, we want to identify what it is we're trying to optimize, in this case maximize. In this case it's the area, so it's just a rectangle, its area is x times y. In this case we do have another constraint, or we do have a constraint on this, that is that the total amount of fencing is 1,400 meters. Okay, well that means if I take that plus that plus that and add them all together, it has to be 1,400. So there's two y's and one x. If I add them up, I get 1,400. Okay, so the goal here, it says we wanted to find the value of x that leads to the maximum area. So to do that, I'm going to eliminate the variable y. So we're going to get 2y is equal to 1,400 minus x. So y is equal to 700 minus 1/2 x. Okay, so that will allow me then to eliminate this variable y here, and so I'll get a now as a function of x alone, which is what I want. So I can plug in the y value that I have right there, 700 minus 1/2 x. And let's just distribute that, so we're going to get 700x minus 1/2 x squared. Okay, so this is the function that's going to tell me the area of this field here, of this enclosed area of the field, as a function of x. So in other words, if I know what x is, if I make x really small, or if I make x really big, this will tell me the area. So again, we can imagine what the graph of that function would look like. I mean, in fact, I can just try to draw a little bit of it right here. This is a as a function of x. Okay, so we can see this is a parabola opening downward. What we're going to end up getting is probably something that looks like this. And again, our domain would be restricted such that we wouldn't have any negative areas and we wouldn't have any negative x values. So this is the part of the graph that we'd be interested in. Again, if I have a very small area, or a very small, x value, that would be like over in this territory of the graph here, my area would be very small, because if I had a very small x value, then I would have to compensate by making the y value really big, and I'd get something that's kind of a long and skinny field. Likewise, if I increase x very large, then I would be making that bigger, and then to compensate and keep the area the same, y would then have to become smaller. So I'd have a long, narrow fencing along the river in that way, and I'd have a small area. The goal again here is that we want to find this nice value of x, which I'm going to call x max, and then corresponding to that I will have another value which we'll call a max. Okay, so really that's the goal, is to figure out what is that point right there. Okay, and again, what we've been talking about, that point is a critical number, so our next step is to take the derivative of this thing, set it to 0. So we'll get 700 minus x for our derivative on that. This is very simple. If I set this thing equal to 0, 700 minus x equals 0 is going to give x equals 700. Okay, so 700 meters is the value of x. That would be the x max value right there. And then I can find, the question asks me to find both the x value that leads to a maximum area and then also find the maximum area. So I can find the a max value. In fact, let me call this x max. I can find the a max value by plugging in the value that I just got into this function here. In other words, this would be a of 700. This would be the value of a that I get when I plug 700 in for x here, which would be 700 times 700 minus 1/2 times 700 squared. If you put that all into your calculator, at least what I got is about 245,000. It's not really surprising that this value would be pretty large, because we're talking about an area here. So this would be in square meters. 245,000 square meters would be the maximum possible area associated with that x value. Okay?